Now, the other thing to note is that beta of the market is scaled very nicely. So if we've got beta of m, we can interpret a lot from that relative to the beta of the stocks. So the beta of the m is the covariance of m with m divided by the variance of m. But what's the covariance of something with itself? Covariance of something with itself is just, it's not 1, not 0. So what's covariance is ex minus ex, y minus ey. If x equals m and y equals m, we've got em minus em times m minus em, which is em minus em squared, which is what? Variance. So covariance of something with itself is just the variance. So we get the variance of the market over the variance of the market, which is, now we get the 1, okay? And that's a nice benchmark to have, because what it means is that we can think of betas above 1 as amplifying movements in the market, and betas below 1 as dampening movements in the market. Okay, so we know from what we did last time that the slope is beta, and for the market, the slope is 1. If the slope is greater than 1, that means the beta is greater than 1. Okay, so if we increase market return by 1%, then on average, the return on the stock is above 1. If we've got a slope less than 1, then beta is less than 1. So the movement in the stock returns on average is less than 1% if the market goes up 1%. Any questions on that?
Can you say that again about it being amplified?
Okay, so beta of the market itself is 1. If it moves 1%, it moves 1%. If the beta of a stock is bigger than 1, what it means is if the market goes up 1%, then on average the stock goes up by more than 1%. So it amplifies movements in the market. Beta less than 1, it dampens them. Other questions? Okay, so that's beta. And what we can do now is we can develop the CAPM. So that's what Section 8 is about. And if you remember, what the capital asset pricing model says is the expected return on a stock or a portfolio or any risky asset is the risk-free rate plus beta times RM minus RF. RM is the expected return on this market portfolio. RF is the risk-free rate, which we usually take to be the Treasury bill rate. So you should read chapters 7 and 8 in the book. So what are these mean standard deviation diagrams all about? What does it mean when we draw that? Well, what's the greatest city in the world? Well, I think most of us would probably agree it's not Philadelphia. It's a very nice city, but maybe not the greatest in the world. So some people would say London, and London is a great city. It's got the theatre, the museums, the history. Now the weather, you know, if you're there for the summer, it may get over 70 degrees Fahrenheit or 20 degrees centigrade if you're lucky, but you'll find out why they don't refrigerate the beer. They don't need to. Paris. Many people would say Paris, the city of lights. Marvelous food, fabulous clothes. Now the people are a little brusque, some might say rude, but it's just the way they communicate there. They don't mean it badly, it's just the way they do that. So there are many wonderful cities in the world. So Rio de Janeiro is one of my favorites. Fabulous scenery. You've got Sugarloaf Mountain. At night you have the Cristo hovering in the sky. It's just a fabulous place. Ipanema Beach, the bodies. It's great. Shanghai, a city of the future. Okay, if you go to Pudong, you've got the Pearl of the Orient, the futuristic architecture. You've got the maglev train doing 420 kilometers an hour. It's very... I stopped now. They reduced the speed. Okay, I used to do 420. But it's very much the future. They don't have... It's like being on the set of Star Wars. They don't have the personal transporters in the sky. But they're coming, my friends, tell me. Now, there are many wonderful cities in the world. Some of you might say Mumbai, Rome, Hong Kong. We can go through lots of long lists. Now, many people would say New York. New York is a blend of all of these things and with its own special characteristics. Now, whatever your thoughts about New York, many of you will end up there because that's still where the best jobs are in the world. So let's fast forward 20 years, okay? Next week, 11:50 p.m. on Monday, they do the deal. They have the budget deal, and now the government can spend. We're not going to have the shutdown. Once they've started to cooperate, we get the ceiling, the budget ceiling, the debt ceiling raised. So things are looking good. The economy starts to pick up. You find it easy to get an internship next summer. And then you get a great job because with the US doing well, Asia starts doing well, Europe recovers, the whole global economy does well. So the teens are a great time. You've got this wonderful job. You're making money. The 20s, things take off in a tremendous way, and we see growth like we've never seen it before, and you're making tons and tons of money. You're richer than your wildest dreams. So then you get to retire. You don't need to work anymore. You have a wonderful apartment overlooking Central Park. You have the ability to give away lots of money to your favorite charities. You can do lots of very worthy things. You have a trophy spouse. What is it that you, as an Wharton graduate, spend your time doing? Is it worrying about what's on at the Met that night? Is it going to Danielle's for dinner? No, as a Wharton graduate, you're worried about your portfolio and where you should invest it and how you should make yourself as happy as possible by investing it. And so when I draw this diagram, that's what you need to think about. That's what this diagram is all about, investing all that money that is there for your retirement. So, you draw the diagram, then you figure out what are your tastes for risk, and then you come up with your optimal portfolio. Now, what you're choosing there is some particular amount of stock 1, some particular amount of stock 2, a whole portfolio. Now, if you were more tolerant of risk, what would your indifference curves be relative to person 1? They flatter, so where would you be? You'd be maybe somewhere up here, like that. Now, we could go through and do that for everybody, and we could figure out their demands for each stock. Now, the problem is that that would take us an enormous amount of time, even if we could get the information. So finding out what people's risk tolerances are is obviously a tricky thing. Finding out everybody's risk tolerance would be very difficult indeed. Now, what people realized after some time, though, is that there's something missing from that diagram. We've got stocks there, but what's missing? Bonds. So let's think about what happens if we add in bonds. Okay, so what we're going to have is our diagram. And we've got our portfolio efficiency locus like that. And let's focus on person 1. So they're choosing X like that. And for the sake of argument, we'll suppose that X has a standard deviation of 2 and a mean of 15%. Now then we have the risk-free. That's the bonds. Let's suppose they're government bonds. And let's suppose that the risk-free is 5%. We're going to put a proportion of our money pi in X, in stocks, and we're going to put 1 minus pi in the risk-free. What is pi here? What's that? How much have you got in this risky asset here? 0. And how much have you got in X? So you've got everything in the risk-free, so pi is 0, and we've got 1 in the risk-free. Now, here we've got everything in X, so pi is 1, and 1 minus pi is 0. What's going to happen as we vary pi? Well, we know from what we did at the beginning, our basic portfolio formulas. So we know means add, and we know that our portfolio variance is given by this. Now, if one of the assets is risk-free, it turns out that we get a particularly simple format.